A2 Maths Conditional Probability. Okay, so before we move on to anything new, what we want to do is just have a refresh of some of the notation that we use for probability and some of the facts that we found from last year. Starting with some basic stuff. So we've got here P of A, and as we know, that's shorthand notation for what is the probability that the event A occurs. So the probability the event A occurs. We can also use a dash. Now that means the complement of A, and it basically means what is the probability that A does not occur. So the probability that A does not occur. Now we also know that if we actually added these two things together, then we're going to have, it's definitely going to happen. Either A occurs or A doesn't occur. There's no middle ground. So if I want to add those two together, I know for a fact that those two added together will have to equal 1. Because number 1 is the probability that it definitely occurs. And we can rearrange that, of course, to write it like this. The probability of A not occurring is equal to 1 minus the probability that A occurs. And you could rearrange that to the other way around as well by swapping these two parts over. We've got this side. This means the union. So the probability of A union B means the probability of A or event B. Alright, so the probability that either event happens or event B happens. So one or the other. It stands for union, like I said. This one here, with the opposite way around, is the probability of event A and event B occurring. So in that one, what is the probability that both A and B occur? And in that one, what is the probability that A or B occur? Right, so there's a difference just by flicking that upside down, changes it around, and that one's called the intersect. And we'll talk a bit more about that when we look at the Venn diagrams. Mutually exclusive. So when we hear the words mutually exclusive, that means that they are completely separate from each other. So the probability of event A and the probability of event B are completely separate events. So if you're looking at the OR probability, it will just be the probability of A plus the probability of B. Because they're completely separate, if you want one or the other, it is just the same as adding the two probabilities. Whereas if we're looking at the intercept of them, the fact that they are mutually exclusive means that they do not intersect at all. So it equals 0. So mutually exclusive means that you could think about how to use this sort of notation to write it in that sort of form. Okay, so mutually exclusive means the two events cannot happen at the same time. All right, so let's go back and look at our addition law. So if I look at this one here, this is the probability of A or B. All right, so we can look at that and we can see that we got the probability of A, the probability of B. We've got the bit in between as well, which is the probability of A and B, this part just here. But we're allowed that because even within there, that is the probability of A or B occurring. This Venn diagram shows the probability of A plus the probability of B. And they are different. Although they look the same, this one doesn't include, only includes this part in the middle once. Whereas if you added these two probabilities together, what's going to happen is you're going to include that part when you added the probability of A, plus you're going to add that part when you included the probability of B. Okay, now how can I get those two the same? Well, this bit in between is exactly the same as the probability of A and B. So this section just in here that's slightly darker pink just there is the probability of A and B. So if I want these two Venn diagrams to be exactly the same, then what I need to do is I basically just need to take that bit away once. Because I've added it twice, I did it once for the probability of A and once for the probability of B. If I take it away once, then those two should be exactly the same. And that's where you can get this from. The probability of A or B is exactly the same as adding probability of A and probability of B. Take away the intersect of them both. And you can see then where that mutually exclusive idea comes from as well, because if they're mutually exclusive, that equals 0, which means that bit's gone, which means probability of A or B equals the probability of A plus the probability of B. So for mutually exclusive, we can see that that part was what we just saw a minute ago. Now you can swap this around. We could add that to this side. We could add that to that side. You're allowed to do that because don't forget, these are just numbers, anywhere between 0 and 1. So we're allowed to change it around like that. and that gives you your two addition rules. So if you had a sort of Venn diagram situation and maybe you knew that fact and that fact and that fact, you can use those to work out the union. Or you may be given the probability of A, the probability of A and B, or the probability of A or B, and you could be asked what's the probability of B. So you can use any three to find the fourth, and that's what we mean by the addition law. Now, none of that should be new. I went through it very quickly because it's stuff that you did last year. None of it should be completely new to you. And if it is completely new to you, it'd be worth going back and having a look over your year one's lessons. Okay, so let's have a look at something new. So we've got a random variable x. Now, what we mean by a random variable is something that just creates a random number. Now, in this case, what can create a random number? An unbiased six-sided dice. If you've got a dice in front of you and you just kept rolling it, that's what we mean by a random variable. It creates a random number, 1, 2, 3, 4, 5, or 6. And if I said to you, what's the probability, looking at the notation, what's the probability that our random variable, in other words, our dice, gets a result that's greater than 3? Now, this is a fair, unbiased, so it's fair, six-sided dice. So to get greater than 3, that means I get a result of 3, 4, 5, or 6. Sorry, 4, 5, or 6, because it has to be greater than 3. 4, 5, and 6 means it's going to get 3 possible results out of 6. And don't feel the urge to write it as a half. You can do, but you don't have to. All right, sometimes it's better not to simplify your fractions. There's 3 possible results out of 6 possible results on that dice. Right, now this is something slightly different. Given that we know that our random variable is less than 5, now what we want to know is what's the probability that x is greater than 3. Now think about this situation like this. Maybe you've got a friend who's rolled the dice. You can't see what the result is in front of them. And what your friend is saying to you, all I'm going to tell you is that this result is less than 5. What is the probability now that the result is greater than 3? Okay, so you need to be thinking about what results could it potentially be, and now what is the probability of your result greater than 3 being that answer. Okay, so let's have a look and see if we can solve it. Here's our results, 1, 2, 3, 4, 5, and 6 on the dice. Now your friend's come along and told you what's the probability that it's definitely going to be a result that's less than 5. It's definitely a result less than 5. So now we know that it's going to be either 1, 2, 3, or 4. So the probability of that happening is 4 out of 6. There's 4 different results out of the possible 6. Now you can solve this just by looking at it. What is the probability now that our result is greater than 3? Now these are the results you know your friend could possibly tell you. In front of that dice, it could either be 1, 2, 3, or 4. What's the probability it's greater than 3? 1 out of a possible 4. That's what we mean by conditional probability. You're given a condition, you're given a situation. In this situation, we're told it's given that it's less than 5. Now that changes what the probability is going to be out of. Before that was 3 out of 6. This time it's going to be 1 out of 4. But what we want to do is we need to have a formula to show this. It's no good just being able to just do it in a basic situation like this. We need to have a formula. So what we're going to do is we're just going to investigate it a bit further. So I know that the probability that it's less than 5 is 4 out of 6. So the chance of what our friend told us happening is 4 out of 6. 4 possible results out of 6 is what it was given out of. What's the probability that it's both less than 5 and what we want, which is greater than 3? Now the probability it's less than 5 and greater than 3 was always just going to be the number 4. Right, and that is the number 4 out of a possible 6 results. Remember, this isn't using that fact just there. We're not doing it out of. All right, so if I just look at a dice in general, the probability it's less than 5 and greater than 3 is 1 out of 6. Now, the probability it's greater than 3, given that we know now it's less than 5, right, we can see it's 1 in 4, is given using this formula. It's the probability of both one event and the other happening divided by the probability of what it's given out of. Now both of those I could calculate. That bit there I calculated because I knew it was just one result out of 6. And that bit there I calculated because I knew the probability to get less than 5 was 4 possible results out of 6. So what does that mean? Well, if I fill these two answers in, that's the 1 out of 6. That's the 4 out of 6. If I times numerator and denominator by the same number, number 6, I'm going to end up with 1 out of 4. It's exactly what I can see there. One result out of 4, but that starts to go towards the formula that we're going to be able to use. So we're showing that formula working. And that's what we mean by conditional probability. Okay, so just grab your notebooks then, because it's the first thing that's new. So a probability of an event A occurring, so that's a P of A. What's the probability of event A occurring given that event B has already occurred? Now that's what we mean by conditional probability, because you've got a condition. B has already happened. Okay. A similar sort of situation is if you're in a classroom and I said, what's the probability of Bill walking in? Now, if you've got a class of 25 people, the probability of Bill walking in is 1 out of 25. But if you had a condition, you said, oh, the next person that walks in is a boy, and you say, what's the probability of Bill walking in? Then it's reduced because you've only got, let's say, 12 boys. So the probability then is 1 out of 12. So having a condition changes what it's out of. And that's what we mean by conditional probability. Now, conditional probability has its own type of notation, and it looks like this. So make sure you've got that down nice and neat in your notebook. And let's just fill in the two bits. So it means, what's the probability of A occurring? All right, so that's the probability of A. Given that, that's what that line means, B has already occurred. And it's absolutely vital you get it the right way round. We'll see in a little while, you get different probabilities if it's the other way round. Okay, so it makes a big deal of difference. In that previous example I said about Bill walking in the classroom, if you imagine someone said to you, given that Bill's walking in the classroom, what's the probability the next person is going to be a male? Well, you know it's Bill, so therefore the probability it's male is going to be 1. So it makes a big difference which way round it's going to be. We can calculate it using this formula. Now that's the formula that we just saw an example of. To work out the probability of A given B, we can work out what the probability of A and B is going to be and divide it by the probability of B. That is why it's crucial you get it the right way around, because what you're dividing by is that bit. Now, one way of thinking about it is look at this as a lazy fraction. There's your numerator divided by your denominator. Your numerator is your A and B divided by the probability of B. So you want to think of it a bit like that. A and B, given that, probability of B. All right, pause there. Make sure you got down what you need in your notes. Okay, so we're going to just do a little bit more work on this formula. And what we're going to do on this formula is just rearrange it so we can see that we could write it like that. At the end of the day, as I said before, these probabilities are just numbers between 0 and 1, so you can manipulate them. So in this situation, what we can do is we can certainly just multiply by the probability of B, and we get that formula just there. Probability of B times by the probability of A given that B's occurred is always equal to the probability of A and B. All right, so just rearranging that formula. Now we can do something more though. If we look at it the other way around, okay, what's the probability that event B occurs given that A's occurred? So that's basically swapping those two over. It doesn't change the numerator because these two, it doesn't matter which way around you put them, but it does change your denominator. Look, it changes it to that. Although I've got B and A, the probability of B and A, that's exactly the same, A and B. Those two are exactly the same. I've just written it around because it fits nicer with this formula. What does that mean? Well, if I times by the probability of A, I get this. But given that that and that are the same, that leads to a nice result. The result of that. The probability of A and B can be worked out by doing the probability of B times by the probability of A given B's occurred equals the probability of A times by the probability of B given that A occurs. So again, same as the previous addition formulas, if you know some of these results, say I know what the probability of B is, the probability of A given B, and the probability of A, I can manipulate this formula to work out that one. Okay, what's the probability of getting a B given that A's already occurred? So knowing that one result means that you can work out some of the missing parts. Okay, so let's have a look at an example of that then. So I've got probability of A, probability of B. So I know what the probability of getting the event A is. I know what the probability of getting B is. Okay, they're quite high probabilities. I also know what the probability of A given B is. All right, so what's the probability of A happening given that B has already occurred? So they are obviously related to each other. So you've got this probability of 0.55. So given I know these facts, can I work out the probability of B given A? Now what I could do is I could just go for these ones here and work out the probability of A and B occurring. Because if I look at the formula like this, I can work out what's the probability of A and B occurring. Because A and B is the probability of B times by the probability of A given B. If I multiply those two numbers together, I'm going to get an answer of 0.418. So now I know what the probability of A and B is. If I know that, can I work out what the probability of getting a B is given that A's already occurred? Right? What's the probability of getting a B given that A's already occurred? Well, I've got that formula for that, which of course is just a rearrangement of these type. So can I fill in the top? Yes, that's 0.418. That's the probability of getting an A and a B. And what's the probability of A out of 0.8? What's my answer then? 0.5225. Similar, but not the same, and that's the crucial bit. The probability of getting an A given that B's occurred is different to the probability of B given A has occurred. They are different answers. Okay, so we'll look at two events being independent. Now you covered independence last year. And just to explain what it means, or remind you what it means, if two events are independent, it means they have no impact on each other. So an example of this could be if you had two dice in front of you, and you say event A is you getting a 6 on the first dice, and event B is you getting a 5 on the second dice. Now, if I throw a 6 on the first dice, that has no impact on the result on the second dice. Just because you get a 6 on the first one doesn't mean you're going to get a 5 on the next one. It has no impact on it at all. Okay? Whereas dependent events could be something like the probability you go to the party depends on whether your friend goes to the party. Right? Those two events would be dependent. You go to the party depends on whether your friend goes. The results on the dice, independent. So that's what we mean by independence. So let's just remind you, independent means that event A does not depend on the outcome of event B. Now think about what this actually means. What's the probability of getting A given that B has already occurred? Now if they're independent, it doesn't matter whether B has occurred or not. That has no impact on the probability of A. If we look at the independent dice that I just talked about, given that I got a 6 on the first dice, has no impact on the probability I get a 5 on the second dice, sorry. It has no impact on it at all. So what we can say is this is where you need to grab your notebooks. If the event A and B are independent, then the probability of A given B is equal to A. And this leads to a great result. A result you may have already seen, and you certainly may have used. If the results of, if A and B are independent, then what we can do is we can use that formula. All right, use the formula we just looked at. The probability of A and B equals the probability of A times by the probability of B given A. All right, so that's the formula we just saw for conditional probability. But what we're saying is if they're independent, this part just here equals just the probability of B. So this comes to the conclusion that if two events are independent, then the probability of getting A and B is always exactly the same as the probability of A times the probability of B. And that's not always the case, only for independent events. So the probability of A and B is equal to the probability of A times the probability of B. And what you can do is you can sometimes use this to prove two results are independent or dependent on each other. Because if you knew that as that result there, that result there, and that result there, so you knew what the probability of A and B is, you knew what the probability of A is, and you knew what the probability of B is, you can show whether they're equal to each other if you times those together, and therefore they're independent. Or you can show that these two don't equal this, and therefore they will be dependent on each other. Okay, so knowing that one fact allows you to check whether results are dependent or independent. Alright, so what I want you to do is to have a go at this yourself. I want you to pause it, have a quick go at this. I'll just quickly run through what you're doing if you need it. You've got different events. Okay, picking a diamond. So if you know cards, great. If you don't, let's just make sure you understand what you're doing. So these results here are all the diamond cards. You've got 13 cards there. 1 of diamonds, 2 of diamonds, and so on. Ace of diamonds, sorry, and so on, all the way across. Event B is the probability of picking a queen. Now the queens are these ones. You can hardly see the Q on them, but they're the queens. So there's 4 of those. Okay, so there's 4 queens. Event C is picking a 4, 5, and 6. You can see those 4, 5, and 6. That's these cards here. All right. So that's your different events, A, B, and C. All right. The diamonds, 13 of those. You've got the queens, 4 of those, and you've got the results of 4, 5, and 6. Okay. Right, so there's 52 cards in total to help you out. And I'm just saying, if one card is picked at random, I want you to have a go at finding those things there. All right, so pause there before you move on or before you look at the answers and have a go at it yourself, please. Okay, then, so let's have a look at this first one. What's the probability I get a diamond, given that I know the card is a queen? Okay, so you imagine it again. Your friend has picked a card at random and they say, my card is a queen, right? What you want to know is what's the probability that person is holding a diamond as well. So the first thing we need to consider is what's the probability of getting A and B? What's the probability of getting a queen and a diamond? Now we know the probability of getting a queen and a diamond is 1, there it is, out of 52. 1 out of 52. Out of, what's the probability of getting a queen? Well, that's 4 out of 52. So 1 out of 52 divided by 4 out of 52, 1 out of 4. Now makes more sense just to try doing it looking at almost like it will be a Venn diagram. So if I look at the first situation, the probability of B's, right? So there's my results just there. Right, what is the probability then? Now I know that my friend is holding just a queen in front of him. What's the probability that I get a diamond out of those? Well, it's 1 result out of the possible 4. And that's what you can do. You don't need to necessarily worry about filling all these bits in. You can see it pictorially, that's fine. If you want to try the other ones yourself, pause there. If not, we'll work through them. Okay, so the probability of getting a queen, given that, so on this one, what's the probability of getting a queen, given that I know I've got a diamond? So again, your friend says, I've got a diamond, so you know it's one of those 13 cards just there. What's the probability? There you go, so it's one of those 13 cards. What's the probability out of those diamonds? Okay, you get a queen. Well, it's 1 card out of a possible 13. So look at the difference between those two. Swapping those letters over makes a big difference to the probability. Okay, what about this one? Probability of A given C. So probability of getting a diamond given that I've picked a 4, 5 or 6. So there's me picking my 4, 5 and 6. That's my condition. All right, I know I've got a 4, 5 and 6 in front of me. What's the probability it's going to be a diamond? 3 out of those possible 12 results. And I can write it as 3 out of 12 or 1 out of 4. It's up to you. Okay, last one. What's the probability I get in 4, 5 and 6 given that they've picked a queen? So again, that makes sense if you again think about it. Your friends picked a card, they say it's a queen. All right, so they got one of 4 cards in front of you. You think, what's the probability that's a 4, 5, and 6? Well, they are mutually exclusive. There's your queens, whereas the 4, 5, and 6 are over here. They cannot be the same. They are mutually exclusive, so therefore it's going to be equal to 0. Why does it make sense equal to 0? Because it's a numerator. Here, the probability of A and B that equals 0, therefore it implies that that must equal 0. Okay, so for mutually exclusive events, conditional probability could equal 0. Okay, so again, I'm going to just pause, give you an opportunity to have a go yourselves. If you want me to run through it a little bit with you, then by all means carry on listening. Okay, so just to make sure we know, the first thing you're going to have to do is fill in that table of results. So you have to do that yourself. You got the events X is picking jam, so there's the X events. There's your Y events, picking chicken, and there's picking cheese. So there are 3 types of sandwiches. You can fill in how many the adults picked, how many the child picked. So this child here, 67 of the children out of 67 out of the 150 picked jam sandwiches, and so on. Okay. Right, what I'd like you to do is see if you can just fill in the table first of all. All right, if you want to fill in the table and do the results, that's okay as well. You can just speed to the answers. It's up to you. Okay, so what we're going to do is just fill this in. Just fill in the ones you can. So for example, I can fill in 150 because I know there's going to be 150 people. These two will go together to make 77. And I've got 150 people in the survey. And now it's just a case of picking out. So I could maybe fill in either of those two. All right, so there's 56. And so because I know it's 56, I can start filling in that one as 33. I could fill in this one now. I could fill in this one. So there you go, 33 and 9 makes 42. I could fill in this one now because 67 and 9 and something else makes 94. And just to double check, these two can go together to make 31. All right, so you've managed to fill in your table of results just there. And now again, it's a good idea to pause and see if you can fill in the answers underneath. There's a bit more going on in this one. Okay, so let's make sure we understand what we're actually being asked. So this is saying, what's the probability of not picking an adult? Well, not picking an adult would be a child, right? There you go, there's the children. 94 of them out of 150. So not picking an adult would pick a child, and I could pick 94 out of 150. Well, what about the second one? What's the probability of A or X? So what's the probability I pick an adult at random, or I pick a jam sandwich? So that could be any of those plus that one there. Be careful not to include the 10 twice. Think about it as the additional one. We've got to take away the one that's there twice, take away the 10. So you could do that, 67 and 10, 10, 33 and 13, take away the extra 10, or you could just add up those 4. All right, if you add up those 4, don't forget it's out of 150. So there we go, 123 possible people out of 150. Right, what about this one? The probability of picking a child at random and that child having a cheese sandwich. So what's the probability to pick a child with a cheese sandwich? So there's the child, there's the cheese sandwich, but this time it's an and, not an or. So I need those 18 there. There was 18 children with cheese sandwiches out of 150. So the probability of one and the other is 18 out of 150. What's the probability? Let's get our head around this. I pick an adult and I don't pick a chicken. Now, if I don't pick a chicken, I pick a jam or a cheese. So what's the probability of picking an adult and the jam and cheese? So there's the adults. There's the jam and cheese. I want the and. So I could have any of those 10 or I could have any of those 13. So to me, that would be 23 out of 150 of them. Okay, right, let's look at this now then. This is where we go move on to conditional probability. So what's the probability I pick a child given that I know I've got a jam sandwich? Okay, so I've managed to pick out, someone said, I definitely got a jam sandwich. What's the probability out of those jam sandwiches, those 77 jam sandwiches, I pick a child? Okay, so that's what we want to look at. There's the jam sandwiches. I've ignored all the chicken and cheese. I've chucked those in the bin. I've only got these 77 sandwiches in front of me. What's the probability that one of those has got a child's name on it? It's going to a child. Well, the answer is 67 out of those 77. Okay, so just doing that rather than having to work out what's the probability of A and X and divide it by the probability of X. You could do it like that, but you don't have to. You can read it straight from the table. It's actually easier. What's the probability of picking a jam sandwich given that I've got an adult? So that's only looking at the adults. The adult comes up to you, so you can ignore the children now. I'm looking at the adults, and I want to work out the probability that adult wants a jam sandwich. Now, there's only 10 adults out of 56 adults in total that want a jam sandwich. So there's 10 adults out of 56, and that's what you can put down. 10 out of 56. Okay, a little bit more complicated. Given that I know I've got a child in front of me, so that's these 94 kids just here. There we go. What's the probability they do not want a jam sandwich? So I don't want the 67, I only want the cheese and the chicken. So it's those two results there. Now put those two results together there, you know you've got 27. There is 27 children who don't want a cheese sandwich. So it's 27 out of the 94 children. Then finally, given that I don't pick jam, so in other words, I'm dealing with the chicken sandwiches and the cheese sandwiches, what's the probability it's not a cheese? Okay, so not a cheese is the same as chicken or jam. Now it's not jam because we know it's not jam. All right, so we know it's going to be those four. What's the probability it's not cheese then? Well, that's going to be those two results just there. So again, drawing it on your two-way table makes it a lot easier to visualize it. Probability of not jam was all of it. The probability of not cheese is that one. So put those together, 33 and 9 does make 42 out of, put all of them together, we'll just add those two, get out of 73. Okay, so just pause if you need more time. Wasn't if you got all those results. Okay, so grabbing your notebooks, please. Grabbing your notebooks, and okay, ideally it'd be nice to print it out. You can cut it down if you want to, or you can reference it in your notebooks to go back to this page in the lesson if you want to just read it. But what we want to do is we want to have a go. So I'm going to pause there, give you an opportunity to write down anything you want or the full question, and we'll have a look at drawing it together. Okay, so the first question is asking us to draw a fully labelled Venn diagram to illustrate this information. Okay, so we've got a sample of 200 students, and there's 3 different methods of going to school, college in this case. They could walk, they could take the car, or they could take a bus. So a Venn diagram would look like this. 3 intersecting subgroups. So I've got the walking group, the car group, and the bus group. Now I might be wrong on my diagram. I might have a situation where the W, the C and the B look like that, go next to each other. In other words, the W and the B's don't cross at all. You don't know, but that doesn't matter because what you might find is if the W's and B's don't cross, you could just put a 0 in there. All right, or you can leave it completely blank if you just fill in the numbers. It doesn't matter. All right, so don't panic if your drawing doesn't feel quite right. It will sort itself out in the end. Now what I need to do is I need to try fill in any of these bits of information. Now you can't just fill any of them in. For example here, 69 answered walk. Now you can tick more than one on the box. So the walkers might also be in the cars, almost be in bus. They might decide that they walk 2 days, take the bus 2 days and get a car the other day. So therefore they have all 3. They'll be in the middle. Okay, so these 69 could be solely walkers, they could be walkers and car people, they could be walkers and bus people, or they could be all 3. So I can't put the 69 in, apart from just having in my head that all of those results has to equal 69. Same problem for B, same problem for W and C, although it's not quite as bad. 24 people said they either walk or take the car. Right? Now walk and take the car is all of this section. because just because they walk and take the car doesn't mean they can't take the bus as well. Okay, they could take all three. So we can't fill in that bit as 24. The only bit we can actually fill in, right, is this part just here that 9 students said they do all three. Because the only one that's all three is that group in the middle, the W and the C and the B. So I can definitely fill in that part just there. All right, it's very easy to look at something like that and think that is only the C and B and therefore put that 45. You need to be really, really careful. So there's our 9 in the middle, sorted and filled in. Right, once we know the 9, what we can do now is we can definitely fill in these ones though. Okay, so we can say that because we know that, we can fill in the 24, the 45 or the 20. That's about which one you pick. So if that's 24 in total for W and C, that has got to be 15. But there's still 24 people in total that pick W and C. Just 9 of them also pick B. Right, so you can fill in the others. C and B makes 45, so that's got to be 36. This is 20, so therefore you can fill in the 11. There we go. Right, so that's those results filled in. But now you've got that, you could definitely fill in your W's, because as we said, the people that put down, these 69 people answered W, also 15 of them answered W and C, 9 of them answered W, C and B, and 11 of them answered W and B. But 69 in total answered W. So there you go. Work out the missing one, has to be 34. So we've managed to fill in all those different results. What about for B? 98, but we could take away that, take away that, take away that, and that would be the result of 42. There we go. I think we're pretty much done. Oh no, there's 200 students in total. That certainly doesn't add up to 200. We don't have the just C's, people that come in cars all the time, and we also don't know what people that didn't do any of them. Maybe someone takes a plane to college or the train. All right, there's 21 students who did not use any of those methods. All right, so maybe there's someone on a skateboard wants to put that down. So we can definitely fill in the 21 outside of these 3 subgroups, but still inside the set of all 200 students. But also, because we know that they all add up to 200, what's missing when we take it away from 200, the answer will be 32. Okay, so very well done if you manage to fill in that Venn diagram. All right, there's a lot going on there. So what we can do now is we can look at the next question. State the total number of students who use exactly one of the 3 methods of transport. So you might have students who just say, we only walk, the students who say we only take the car, or the students that say we only take a bike. All right, not the combos. All right, now you can do it using all the different numbers at the top, or you could just actually work it out for the Venn diagram. So the probability of walking but not car and not bike would be that one. The probability of not walking, not biking, but definitely carring. Notice it's an and. And the probability of bike but not walking and not car is that one. All right. And do not forget that each of these results is out of a possible 200 students. So you've got a total there of 108 students that do exactly one form of transport. But 108 students would be out of the 200 if they wanted the probability. Now, I do apologise, it was just asking for the total number of students. If they wanted the probability, it would have been 108 out of 200. Okay, I just rushed on a bit there. I do apologise. The probability of C and B occurring given that W has already occurred. So let's get our head around this. Given that the student has said, I walk, okay, I definitely walk on some of the days. What's the probability that that walker, that student that walks on some of the days, also does C and B? Also does C and B. So it's this one just here. The probability that he walks, what's the probability of this bit as well? Given that we're only dealing with that set. So this is how we could write it. This is how we need to think about it. Given that I've got a student that walks, so that's all those results just there. I can add those together. I don't need to. I know it adds up to 69. Okay, so out of those 69 students, how many of those were also C and B? Well, it's going to be those 9. 9 students out of the 69 is the answer they're looking for. And you can only do that because you managed to fill in the Venn diagram earlier on. Okay, so we looked at two-way tables, we looked at Venn diagrams. Now we're going to look at another method where we might use conditional probability, and that's if we have tree diagrams. So what I'd like you to do, please, I'd like you just to have a go at drawing that down and writing down or showing it on a tree diagram. Okay, so on a tree diagram. Now you might want to just do it yourself, that's fine. You might want to wait to get my first hint to you. It's up to you. Okay, if you don't want a hint, pause it there. If you do want a hint, my starting position was like this. Either the bread is okay or the bread is mouldy. That's my starting position. You can go on from there. You take a bite of this 4-year-old sandwich because you're really hungry, and the first thing you can check is whether the bread is mouldy. Right. Once you've checked whether the bread is mouldy, of course, the next problem is the cheese mouldy? So for each of those situations, the bread might be okay and the cheese might be okay. The bread might be okay, but the cheese will be mouldy. The bread's mouldy, but the cheese is okay. Or the bread's mouldy and the cheese is mouldy. So you could have any of those situations. But even if you get the bread okay and the cheese okay, you've then got to face the ham. And the ham could be okay or mouldy. Right? So you've got this type of situation. Right, what we can do now is we can fill in some of our results. Just be aware, if you've got your dashes the other way around, it doesn't matter. As long as you put down some sort of key and say that dash means mouldy, then you'll be all right. Okay, maybe on yours, dash means okay. It's up to you. All right, so the first thing we're going to face is the probability that bread is mouldy is 0.7. So I can put that down as 0.7. That means that has to be 0.3 because it's either mouldy or not mouldy. Right, now the next bit is dependent. These results depend on these ones. If the bread is okay, there's a better chance that the cheese will be okay. If the bread is mouldy, maybe that affects whether the cheese is mouldy. So let's just get our head around what it's saying. If the bread is mouldy, that's this one, then the cheese would also be mouldy with a probability of 0.6. There you go. So that's going to be 0.6. But the cheese will be mouldy with a probability of 0.2 if the bread is not mouldy. Okay, so I know that if that's 0.3, because it's not mouldy, then the cheese will only be mouldy at 0.2, so it's not too bad. Generally, the cheese will be okay if the bread is okay. I can also fill these in though. If the bread is mouldy, the cheese will be mouldy with 0.6, not mouldy with 0.4. So you can see there are different events depending on the bread. These are definite dependent events here. Right, what's the next bit? If the cheese is mouldy, so that's there, then the ham will also be mouldy with a probability of 0.8. So the ham is affected by the cheese. It's not protected by the bread. So the ham is mouldy, the cheese will also be mouldy with a probability of 0.8. So I can fill that in. Also, it'll be mouldy with probability of 0.1 if the cheese is not mouldy. So it all depends. So 0.1 if the cheese is not mouldy, so that's great. But it'll be 0.2 and 0.8 if the cheese is mouldy. Okay, so just getting your head around which ones it is. These two are going to be the same, of course, because they're only affected by cheese. So you just need to be really careful when it comes to actually filling in your tree diagram. And of course, you might have had the ham first and things like that. It depends. In this situation though, because the cheese depended on the bread and the ham depended on the cheese, it made more sense to write it in this way. Right, once we've done that, of course, you now can actually fill in all the possible different combinations and the probability those combinations happen. That's the good thing about a tree diagram. It means that you are systematically working out every possible combination of results. So I know that it's either everything's okay like the ham, the cheese is mouldy, the cheese and the ham is mouldy, just the bread is mouldy, and bread and ham is mouldy, bread and cheese mouldy, but ham okay, and then everything mouldy. So there's all 8 different situations. Once I've got those, I can work them out. 0.3 times 0.8 times 0.9, remembering that it's going across when you're looking at these situations. So with the probability that bread's okay, cheese okay, and ham okay means I'm timesing across and getting 0.216. Okay, I'll do the maths for you. 0.3 times 0.8 times 0.1. Done. 0.2 times 0. Sorry, 0.3 times 0.2 times 0.2. 0.012, and so on. Okay. Seeing the biggest thing that's likely to happen: bread mouldy, but cheese and ham okay. All right, that's the most likely situation. Right then. So I've got all the possible answers in front of me, and what I'd like you to do is I'd like you to have a go at these questions. You might want to do it, pause, have a go at answering it, seeing if you get the same answer. So my first question is this. All right, what is the probability that exactly two parts of the sandwich is mouldy? Okay, so pause there, have a go at working that out. Okay, so exactly two parts. So no, 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 yes, cheese and ham. No, oh yes, bread and ham and bread and cheese, but not the bottom one because I want exactly two. So there we go, those three events. What's the probability I get any of those three? You add those together. You times when you go across with the tree diagram, you add when you go down. In fact, if you added up all those results, no surprise, it equals 1. Okay, try this one. Pause there then. Okay then, given that the ham is mouldy, write down the probability that the bread is not mouldy. All right, so this is thinking of conditional probability. So we need to make sure we get our head around this. Given that the ham is mouldy, so I'm only looking for the ones where the ham is mouldy. So I'm only interested in that one, that one, that one, and that one. Because I know for a fact the ham is mouldy. Someone's taken a bite and gone, the ham's mouldy. What I want to know now is, can I ditch the ham because the bread's going to be okay? So which one of those, out of those 4, is the bread okay? Well, I would say it is that one and that one out of those possible 4. Right, now don't do divided by 4 because there's 4 different events. It's the probability of those 4, the probability of those. So you can add them all up. Okay, that's the probability of the ham being mouldy. The probability of ham mouldy and bread okay will be that one and that one. So it's those two added up, divided by all 4 of them added together, and that's the answer you're looking for, 0.165. Okay, there's your probability of both ham mouldy and bread okay. So that's that and that, divided by the probability of ham mouldy, which was all of those. Okay, so I've got that one, pause it there. So given that the ham and cheese are not mouldy, what is the probability the bread is also not mouldy? Okay, so just pause with that one. Okay then, so I'm looking at the sandwich, I'm saying, yeah, ham great, cheese great, both of those are okay. Which ones are those? Cheese and ham great. Cheese and ham great, everything else has got a bit of mouldiness. So it's those 2 results. Okay, what I don't know is about the bread, but I want to know what is the probability that the bread is okay. So that one there, all right, that the bread is not mouldy. So that's me, that would be 0.216 out of those 2 added together, because the probability that the cheese and ham is not mouldy would be those 2 put together. All right, and I want the 0.216 out of that put together. Okay, what do I get? 0.462. Not a bad probability. Do not forget that's given that the cheese and ham is already okay. Right, given at least 2 parts of the sandwiches are mouldy, what's the probability that bread is not mouldy? So again, pause there, see if you can work that one out. Okay, let's have a look at this then. Given at least 2 parts of the sandwich is mouldy, so someone's looking at the sandwich and going, right, we've got ham and cheese mouldy, we've got bread and ham mouldy, we've got bread and cheese mouldy. We could have all 3 of them mouldy because it's at least 2 parts. So it could be any of those 4 situations that you've got in front of you. What you want to do now is you want to find out whether the bread is okay in those situations. So the only one of those situations where the bread is okay is that top one, the 0.048. You can add those 4 together to get you the probability of at least 2 parts of the sandwich not mouldy. And then you're looking at that probability 0.048 divided by 0.496. That gets you an answer of just under 10%, 0.097, just there. Okay, so it looks like a lot of work to do, and that's because you've got a bit on Venn diagrams there, you've got a bit on two-way tables, you've got a bit on just rearranging and solving using the conditional probability, but you've also got some tree diagram work. So there's a lot of work to do there. So what I would say is go away, have a go a bit on each, try to do some of the harder questions, and then go back and do a bit more. So try to mix it up a little bit. Okay, have fun.